Hello, I am Arka Ghosh. I'll be talking to you about SDN based flow monitoring and the flow characterization classification based on which we've done the project and which we'll be demonstrating. So I'll straight away head to uh, the importance of this topic in real time situations. Say SDN-based flow monitoring is an integral part of traffic engineering, and it is used for, say, identifying different kinds of threats and also decide on the quality of service to be used. And say, for example, to categorize different kinds of applications based on their traffic characteristics. So this project is based on mainly tapping, virtual tapping system we have used to extract the packets and then characterize and classification based on the applications. So I will take you through what virtual tapping is. Virtual tapping is a software-based method to capture copy of the packets flowing between two nodes in a network. Uh, the approach that we've used here is a passive method. So, and why we are using a passive method is because in order to analyze the packets offline without affecting the real-time traffic in the network, we generally use passive approach so that the loading on the network is lesser. Uh, and say we've used the internal ports of the OpenV switches for the tapping purpose, for the passive method of tapping purpose. Why we use that? Because we found the OpenV switch has an internal port as a readily available resource. We found in various documents that this can be used as a method for tapping. Now I'll take you through the network topology that we've deployed in our demonstration. This is basically a ring topology with 4 switches and 4 hosts connected to each switch. So this is generally used for various most popular used topology in the industry and the world. So I'll take you forward. Here's an example of the upscaled network topology based on the topology that we showed you. I am showing this to you to demonstrate how we decide where to do the tapping. Basically, we'll prefer to, our choice will be preferred based on the switch which is at the edge of the network, that is adjacent to the host for the tapping. We choose this because there are two reasons. One is in order to impose lesser loading on the network, and also provide more accuracy to the extracted packets. Say for example, we want to extract packets which are flowing between H1 and H2, or say H1 and H3 in this case, then we'll prefer to tap either in switch S1 or S3. So I'm talking about this scenario where being all the network elements being hosted by a single VM. Now taking you forward to another situation where various elements will be distributed among various other VMs. In this case, we'll still stick to the method of selecting the edge of the network for the tapping location, but we need to keep in mind the utilization factor of the VM. Say for example, in VMZ, we'll first of all see whether the CPU utilization is high or not. If it is high, then we'll probably have to go back to switch number 7 to do the tapping. Now we've known how to do the tapping process, where we'll do it. Now I'll take you to, say, the controller that we're using. It is Open Daylight that we are using here as the network controller. It seems to be more stable. It has a few GUI features we've used pretty well in our deployment of the project. We've used the REST APIs, which can be deployed using the GUI, and we can also view the JSON outputs using the GUI. This stood out for us while we used the ODL. Now I'll tell you how we have decided on when to do the tapping. We've developed a code or a script for this. This script basically queries the Open Daylight about the topology. It returns a JSON file as a response. we read the JSON file and take out the node IDs and the connector IDs, and we use these node IDs and the connector IDs to query the Open Daylight for specific node based and connector based uh, flow count, and we stored them in particular variables, one set before and one set after a particular time duration. We catch the difference of these two variables, and we can find whether the transmit and RX byte count are increasing. If it is increasing, then then we know that there is some traffic in those particular nodes and connectors, and then we can go for selection of the tapping point. If there is no traffic, then we'll wait for when the significant traffic has increased, and then we can go for the tapping. Next, we will demonstrate how we are doing the tapping, and also the flow characterization and classification.
I'm going to show a demonstration on the various applications that we have used for the flow characterization and classification. So we have deployed the topology as shown in the previous presentation, and to make sure of the connectivity, I just pinged between the various hosts. In order to simulate the UDP and the TCP traffic, we made use of the iperf tool in order to simulate the packets, a TCP and the UDP packets with the different bandwidths, window size using the user-defined port number, etc. And iperf even provides an facility to mention the DHCP value, that is a type of service value that we need with the minus S option. So we made use of the iperf tool in order to simulate various UDP and TCP traffic. Now the next major application that we have taken is the VoIP. VoIP has become an important application in our day-to-day life, and in internet perspective, like various Skype and business calls are made for both official and personal purposes. So in order to simulate the VoIP packets, I have just used the SIPP in the Linux in order to simulate the uplink and the downlink voice packets similar to the real-time traffic by making use of the codec G711, which is a widely used codec. So I'm just going to start and listen the server in host 1, and in host 2 I'm going to start with the call. So we can see that with the invite 100 ring, 180 ringing and 200 OK messages, that the SIP has been established and a VoIP call has been made, and the RTP packet started flowing in both uplink and the downlink direction, which is similar to that of the voice packets between the host 1 and host 2. Another major application that we have demonstrated is making use of the video streaming through the VLC wrapper in the Linux. So just quickly show a demo like how to run the video in the Linux environment between the two hosts in the mininet session. So I'm going to stream it from the host 1, and I'm going to play it from the host 2. So in the host 1, you can just stream. We have an sample MP4 file. Stream it. Here for video, we can use the RTP MPEG transport stream. In case of an audio file, we can use RTP audio video profile as well. So add it, we have to give the host 2's IP address, and the base port is going to be 5004. And here for video, we can choose H264, which is again an internal codec for video. And in case of audio, you can choose the MP3, MP4 format. So just keep it ready to stream in the host 1. And from host 2, since we know that the 5004 port has been defined in order to stream it, we will listen on the same port from host 2, and we just play it, and here we stream it. In this way, we can run the video file between the two hosts. That's like we can stream and play it in between the two hosts. So another major application that is widely used is the file transfer. So here we make use of the FTP file transfer procedure. Through FTP we can even upload or download the packets. So I'm just going to do the FTP. For in order to the previous requirements for the FTP will involve listening on the ports 20 and 21 that can be started via the exnedit, and I have just created a local user in order to store the files to do that upload or download. So here we do the mget and the file name in order to start with the FTP file transfer, which is like the on top of the TCP. So similarly for HTTP traffic, we have just written a script in order to start listening on the server port 80, and from the host 2 perspective, we will be like do the wget every 1 second in order to query the HTTP server, and in this way we will be able to simulate the HTTP traffic as well. Now let me demonstrate the script that we have written in order to show the switch and the node connectors whenever there is a real-time traffic that is running in the background between two different hosts. Let's say once I start the script, it shows the different switch IDs and the node connectors, and since there is no traffic, it says there is no traffic. Once we start the ping, we can see that the node connectors and the various switch IDs which are involved in the traffic is shown.
Now I want to show like how the tapping process is done. We can even automate it whatever we are doing it manually. So if you do the OVS VTL show, it will show the list of bridges that is available and what are all the ports concerned, like the internal ETH3, ETH1 and ETH2 are the four different ports available in S4. So each one is concerned with a separate port ID, which can be listed with this command. Um, so here we see like there are four port IDs. Each one is concerned with the port. It is a direct one-to-one mapping available. Now we will create a mirror and we will assign the incoming the traffic in E3 and the outgoing traffic in ETH1 as a source and destination. And as well as we will assign the internal port as the mirroring port in which the packets can be like collected for further analysis. So the commands used for that is in order to create the mirror and add it with a bridge S4, we can do this above command, which will create the mirror called my mirror and add it to S4. After this, we can add the source and the destination ports with the E3 as the source and ETH1 packets as the destination one. After this, let's assign the internal port of S4 as the output port, which we can do it in this way. And after that, you can list out the information of my mirror, so which will show the output port as the internal port, a destination port as ETH3 and source port as ETH1. So once there is a real-time traffic that is flowing via ETH3 and ETH1, it gets mirrored in the output port, which is nothing but the internal port, and the statistics will get incremented during the mirroring. So, in order to delete the ports, we can just do the clear of all the mirrors that has been created in S4, and in this way, we can clear all the existing mirrors.
Hi, after tapping from the internal ports of the switch, we collected the dump which has all the network traffics between the concerned host. This dump is converted into a PCAP file using a Wireshark, which in turn converted into XML, and then it is converted into CSV for further analysis. By using Python and Pandas as a data analytics tool, I programmed. So let's wait for it to complete the run. As you can see from the output, of the traffic characterization, the table shows different match fields as characteristics of the flow, which was listed from the OpenFlow 1.4. Even though there are 41 match fields, we have taken a subset of 11 out of it, and it can be extended for the remaining fields as well. Here, we have seen different types of MAC addresses, source and destination IPs, protocols, and different types of source and destination ports. Based on the classification and the match fields, we just found out different types of protocols like TCP, UDP, and ICMP. Based on the characterized flow, we further analyzed to bring out the statistical data comprising of classified traffics based on the different types of applications that has been run. From the table, we can see that UDP and TCP are the underlying protocols, on top of which the application protocols such as RTP, HTTP, and FTP are run. We can see that RTP, which is the real-time protocol, can again be classified based on the payload types like G711 codec for VoIP service, MPEG 233 for video stream, MPEG 214 for audio stream, and FTTP protocol FTP protocol which port number 20 and 21 for file transfer and port 80 for hypertext transfer protocols. Thank you.